Hi, everyone. Thanks for joining us this afternoon. This is the Apricot tutorial session presented by Thomas Wang from Cisco. He's going to tell us about SRv6 with some tech updates, use case, and operations. When you're ready, Thomas.
Thank you, Anthony. So, how's everyone? Like, hopefully you enjoyed the day. And for me, I'm pretty happy to come in here to doing this SRv6 tutorial. The reason is, I'm not sure how you're feeling, it's just because the day for the country, for the weather, and I'm coming from Canada. So for me is a good, perfect perfect place and perfect weather. Okay, so as what we has been showing on the screen, we're going to talk about the SRv6. And SRv6 is different from all the MPLS. It's kind of a build up on top of the IPv6, and we see more and more demanding from the IPv6. And before we start, I do a little bit introduction for myself. So I coming from Cisco system, and my background is on the R&D. So I work in Cisco R&D team for 18 years before I joined with the marketing team. And my current position is the technical marketing engineer of the ASR 9000. But I mean, my main background is on MPLS. So basically, I did for all the MPLS traffic engineering, RDP, segment routing, and segment routing V6. That what we're going to introduce for today. And I'm also doing quite a lot for large enterprise support, like major banks. And that's federal, public sector. That's my main territory. Okay, in today we're going to cover, for SRv6 fundamentals. And then we're going to talk about the microsegments. So the SRv6 is kind of the new innovation for IPv6. And in order to make the forwarding more efficient, that microseats we has been, to get in. And with that, we're going to introduce how we kind of doing the forwarding with microseats, right? So basically, we will doing, how to define the microseats, how we do the ship lookup forwarding. And then after that, we have like a few use case we're going to cover, right? Like a VPN over SRv6 and how to do the protection, right? And then how you doing the traffic engineering to get the traffic flow steering. And last not the least is the FlexArgo. So basically, in the MPLS, we have these kind of affinity, right? Try to engineering your links and how to control the traffic going to utilize the different kind of SRG or the different coloring, right? Similarly, we can do that with the SRv6. Okay, so let's talk about these fundamental things for SRv6. Before we start, I wanted to give a background, right? Like a lot of use case or the customer has been deployed in their network is MPLS. So MPLS infra is already there. We do a lot traffic engineering. We do RDP, we do RSVP, and we do the segment routing as well, right? Segment routing is basically we rely on the IGP to allocate the label. So a lot of protocol we can allocate the label, leverage on the MPLS infra, right? But SRv6 is different. It's built on top of the IPv6. It's the IP lookup. But we has been defined SRv6 with the function we wanted to, carry over the IPv6. So here, a few of the important things I wanted to highlight for SRv6, right? The most important thing is we're going to build up a stateless IP fabric. So the stateless, why that, important? If you do the RSVPT, you're probably understanding for every single tunnel, for every nodes in the network, you have to create RSVPT with the RSP session, with all the different nodes, especially in the core, right? If you have like 100 nodes, and if you create a tunnel, between all the 100 nodes, you easily to get into this core scalability issue. We call it N-squared scalability issue, right? So that's why we bring in the segment routing, we bring in SRv6. We wanted to use the source routing and just get rid of those signalings. You're not going to facing this core signaling issue anymore. Okay, so here is what we has been built up for the IPv4, right? Like we build up IGP, and then in order to do the label forwarding, we have involved RDP, right, for the label binding. And if you wanted to do the traffic engineering, we get into the RSVPTE, right? And then if you want to support a VPN service, right? And then you bring in the, BGP, VPN v4, VPN v6, right? A lot of stuff has been built up, in the different layers to kind of, support these things. This has been very successful for the past 20, 25 years. Nothing wrong with it. But the only part is IPv4 is a short IP header, 32 bits, right? Everything you have to use a different protocol in order to do these kind of network different layers to build up these function, right? But it's complicated, right? If you maintain operation this network, you need expertise for routing, expertise for MPLS label forwarding, right? All these things. What if you deploy the IPv6, right? If you want to build up IPv6, did you want to reinvent for all those protocols with the different layers again on IPv6? Like we're talking about RDP, right? RDP implicitly you understand is for IPv4. We talk about IPv6 RDP, like I think 10 years ago, right? Like different vendors, they under the discussion, pretty much, they decided to say that's probably too much work to rebuild everything, just for IPv6. And that's how this SRv6 get in to so, creatively to resolve the problem and building with the traffic engineering, building with whatever we call the service labels, right? This is how the SRv6 to be becoming more mature, more adopted by the industry. Okay, so what is SRv6? Basically, we can say, we're going to simulate SR MPLS label stack. So we can say we have the source address, we have the destination address, and if we wanted to create engineering, right, you need some like explicit path. The explicit path you need to put it into a kind of a stack, right? You're going to let the forwarding to say, I'm going to travel node 1, node 3, node 5 until going to my destination, right? In order to do that, you need kind of to build up these, okay, so I try to use my mouse, but maybe that's not working well. Okay, yeah. So, okay, right here. Okay, I probably can use my finger to point. That's so easy, right? Okay, so as you see here, right, we have the source address, and we have all the different, the node list you has been put in, right? But this is kind of original SRv6 proposal. The only part you have to stack up for all the IPv6. Each IPv6 is 128 bits, right? But I mean, the concept, the forwarding is all good because you have a stack of IPv6 led nodes to kind of doing this traffic engineering so that you can, manage in a way like the MPLS we did before, right? So let's begin with this. Okay, now we're going to talk about the macro seeds, right? Macro segments. Why we need a macro segments? So we wanted to kind of more efficient to use the 128 bits so that we can make that, overhead more efficient. And Cisco create these macro seeds, and the abbreviation is like a USEED, right? And the IETF standard, they call the compressed, next compressed seeds, right? So I coming from Cisco, and for this tutorial is purely technical, right? I don't want to kind of get into, how the termination, how the different names. That's all fine, right? Let's just focus on what we has been trying to resolve. Is that make sense? How these things working in the industry? Okay, the macrosys we try to do is for 128 bits, we wanted to define a few things we call the locator. The locator will be involved locator block and locator nodes. And then we have the function, right? And of course, this is arguments is kind of optional, but I mean, if you need to input certain parameters, that is there. The mechanism is there, right? And with this definition, the good thing is you could have defined multiple domains. The multiple domain will be help you to say, I have a domain has been defined so that I can have 100 nodes within this domain, right? To do all these we call macro seeds identification for the nodes. And how this works is actually if you don't have compression, right, on the left side, right? Even the domain is common, but you still need to have a list of 128 bits, try to giving a segment list, right? And then on the right side, you can see if I have a common block, and then if I give the nodes identified by the 16 bits, that will be more efficient, right? For example, if I have this 128, I call this container. This container at the very beginning is 32 bits as the block. And then I have 6 nodes will be easily to carry on in this segment list, right? This is called compress. This is making these 128 bits more efficiently. Okay, so let's give another close look how these macro segments looks like. It will be called format 3216. It doesn't have to say your block have to be 32 bits. If you like it, you can define the block with a larger, more scale. If you wanted to have like 1,000 nodes, you can have 48 as the block. But with Cisco, we define with the 32 bits block locator is kind of good enough and make the 16 bits like the next 96 bits, and you can easily insert for 3 nodes list or node stack into 128 container. So we feeling this is more kind of be efficient way to define the macro seeds. So the format we call 3216, right? But I mean, different vendor, you can select the different block, how to define your block size or the node seeds. But node seeds, typically if you wanted to do the interop, you have to follow the 16 bits, right? Even the blocker can be big, but I mean, the node identifier should be the same. And with that, now we can revisit this, technology, right? If I have my block, I have my node ID, and I wanted to have this kind of define traffic engineering path, and I can put it in, right? Within that block, I have node 1, 2, 3, 4, 5, 6, and my traffic will be follow exactly going these kind of the segment node list so that I can do the traffic engineering. And this will be save a lot header space, right? Because we compressed 6 nodes within one of the 128 container, right? So that's the Mako 6 is benefit from. Okay, so with that, now we can see if we define the core as SRv6, if my CE site is worth IPv4, I can carry over a IPv4 container over a core SRv6, right? That's all possible, right? And with that, we can see if you have 6 nodes, we can put it in one container, right? But what if you have more, right? For example, if you want to have a 12 nodes, you have to put another 16 in the segment list, right? But in this example, we try to say we can easily support 18, like an 18 label stack. Think about MPLS, right? Like normally the forwarding they can handle the IP label stack is 6, right? Because you don't need more than that. In the traditional MPLS, what label you need? You need LDP label. You probably need the RSVP label. You probably need a fast reroute label, 3 label, and then plus the VPN service label. 4 label enough for traditional MPLS infrastructure, right? And then Sigma routing get involved. We say we can define our more deeper label stack, but basing the hardware capability, usually it's just about 10, maybe. I'm working on the Cisco ASR 9000. We can support up to 12 label stack. And within this, you can see we can easily support up to 18 traffic engineering paths, right? This is already super or better than the traditional MPLS infrastructure. Okay, so now this picture telling you with these macro segments or compressed seats, how the the overhead efficiency looks like, right? If you without the compression, that's the upper curve has been all the way up, right? The more 128 bits to put into the segment list, the less efficiency will be. And with the compress, you can see, right? I have like 6 nodes. If not enough, I put another 6 for 12, and then the later on 18, right? If you want more, yes, we can do. But I mean, 16 node paths is quite enough for traffic engineering, right? Like considering you have like 100 nodes in the network or even larger with 1,000 nodes, I mean, fair enough, fair enough. And also important, you are located by the node prefix. That means it's unified in the domain. You just need to give one node identifier. You can travel everywhere within the network domain. Okay, so we finished this, the definition for SRv6. We finished the definition for macro segments. And now we're looking at how we flood it, how we gathered those information to be, populated in your network so that every nodes they can easily to address the nodes in the network so that we can do the forwarding. Everything is rely on IGP, right? It's still rely on IGP, right? If you're talking about the traditional MPLS, can you do these things at the MPLS infra? No. The MPLS infra is built up on top of the IGP. So basically, IGP do all the routing converge, right? Then LDP involved to allocate the label, banding the label to a prefix so that you can do the label forwarding, right? This is LDP. And then you introduce the RSVP-TE. The reason is you wanted to have the bandwidth reservation, right? You need to have this fast reroute, and you need some explicit paths, right? This is RSVP-TE. And everything, those information flooded by IGP, right? But in today, we can have these SRv6 to be defined in the IGP. So ISIs, they're going to define the SRv6, and also they can flood it SRv6. Once you flood it, and this is what interesting to hear is, if I have 3 nodes, right? Node 4, if we flooded my identification to all the other nodes, right? And other nodes can locate me, but I have two things defined within the same node 4. On the left side, I have a short IGP path. On the right side, I have low latency. How you get low latency, right? I think this is kind of the very creative way to get IGP to do better forwarding is based on the latency, because traditionally we're always looking at IGP matrix, TE matrix, affinity, right? Or SRg, right? But if we wanted to have the short latency, you need to measure, right? So that's how we have another protocol just try to measure every single hop on the link. What's the delay? And you flood all the delay information to every node. Then, from node 5, if I wanted to reach node 4, on upper pass, it's short IGP as traditional. But on the bottom pass, it's the low latency, low delay pass. And these will be benefit to a lot of financial customer, right? Think about a lot of financial customer or even the trading company, they always prefer the low latency. And this has been already built into the SRv6. Okay. With that, we know how the SRv6 define. We know how the macro segments to be efficient utilized for IPv6 header. And then let's look at the forwarding. So you define everything, and you wanted to show how these things will be drive for the packet, forwarding. Okay, in order to define the SRv6, right, you need the configuration in the IGP. The IGP will be having every locator to be defined, right? So for example, we have the main locator for short IGP path, right? And we have another locator is for the latency path. And we have been to define this inside the segment routing so that we have defined, the main locator, the low latency, and you have to assign a prefix. So basically, a prefix like a loopback on the nodes. And this loopback will be help identify for a unique nodes, right? But one nodes, you could have a multiple matrix associated. Let's say the loopback 0, you are using for short IGP path. And loopback 1, you are using to identify low latency. I just giving this example, right? When you're flooding one for short IGP locator, and the other one you flooded for the low latency locator, right? So that's how you kind of build up to define the SRv6. And within the SRv6 now, we going to be, flood those information, and we can go through with the IGP. And with the IGP, and we can see, so the IGP will be, just let you to say, I'm going to flooding the main, I'm going to flooding the latency. Once you enable in the IGP will be generate all those locators. And those locators is actually associated for the prefix, right? When you define the SRv6, you define the prefix. And that will be having those prefix associated to the locator flooded out in the network, so that the other network nodes, they can rely on this unique prefix or the locator to finding the path to the source node, right? If the source node just flooded with short IGP, right, you only can addressing with the short IGP way, right? But if you flooded with low latency affinity, then You're giving the whole network with the different way how to locate the source node, right? This is how you build up low latency paths, shortest IGP paths, and also the traffic engineering affinity. So that's how this SRv6 to be work in the IGP flooding. And in this example, as you see, you have the main, and you have multiple function, right? We call the introducing the microsegments. So one node is having a node locator, but they also allocate the function. For example, IS is the function. You have one microsegments allocated for IS adjacency. So basically, you say within that like adjacency, you're giving the microsegments. You can forward on the ISS adjacent top one, first one, or the second one, right? Each ISS adjacency, they also associate with a microseeds segments, right? And so do the BGP. If you define a BGP worth, and each worth will be allocated one microsegment. And if you addressing to that node, right, how that node will be forwarding. For example, if you have a VPN package coming to my node, right, if I know that function is using that macro seeds, and I see the macro seeds is actually allocated for BGP worth 1, and yes, I'm going to look up the packet according to the BGP VPN for that worth 1, right? Make sense? This is how the whole theoretically hierarchical to allocate the label, define the macro segments, and then flood it, and then you can always try to carry on the traffic accordingly. How you check those information, right? And this what we has been defined, show segment routing SRv6 manager. I don't know, the other vendor may have different way to telling this, but this is how we telling in the Cisco. Once you define the SRv6 config, once you has been using IGP flooded, right? They always telling you what's the block, right? The block on the top, and what's the format, right? Block 32 bits, node 16 bits identification, right? How many domain you has been defined, right? For example, you have defined 3 domain, and they will be telling you each domain. And more important, on the left side, what's the function you're going to do, right? You're going to do the, VPN v4, VPN v6. Are you going to do per CE label allocation, or are you going to do the per verb label allocation? And you see that they had the DT and they had the DX. DX is the cross connect. That means if you do per CE label allocation, it's the DX. If you do per verb label allocation, it's the DT, right? So it already telling you once you have the macro seeds reaching to the nodes, what kind of the lookup they're going to do. And all these will be flooded by the IGP, and you can always using this show segment routing SRv6 manager to get all those information from the database. Okay, once we have that, right, we already understand, define the SRv6 macroseeds to make it efficient and rely on IGP to flood it. Now let's looking for one example. I wanted to show you how SRv6 forwarding going to be looks like, right? I'm giving a very simple way. I'm going to giving you a static label list. Is that sounds familiar? That's traditional MPLS, right? But I mean, we call the segment list. But why I wanted to give this static, because if you work on the MPLS before, you can so easy to understand this. You define a segment list. The segment list will be giving a list of the microsegments to telling you how many nodes you're going to travel to reaching to the destination, right? Once you have this segment list defined, you define a policy, SRv6 policy. And the policy will be telling you the behavior to do. So the behavior they are showing here is just telling you, are you going to do the penultimate popping, or are you going to do the alternate, decapsulation, right? But most important thing is with that SRv6 policy, you're going always follow for that, static segment leads, right? So once the SRv6 policy has been created, if you do show the policy, you can see exactly the policy will be followed and with exactly the segment list you has been defined. Okay, now we kind of having SRv6 policy is created on the router 12. The first node on the explicit segment is router 1, and then router 3, all the way down, right? And with that encapsulation, how you forward. So basically, the source node is router 12. They giving a static segment list. They encapsulate in this packet. The packet header already telling them to travel with the first node, router 1, right? And then router 3, and then after. Once you reach into the router 1, the router 1 will be checking on the segment list to say, hey, this is for me. If I see this is for me, I have to looking to do an action. And this action is basically I do a shift and lookup. What do you mean shift and lookup? Okay, so the story is here, right? Let's say I finish the first node, router 1 sending to the router 3, right? And router 3 will be do the same function, do the same operation again, right? So what's the real thing they do is the router 3, once they getting the node 3, they say, okay, this is sending to me. I'm going to shift 16 bits. If I shift on the left side 16 bits, the next router 5, they're going becoming as the active, the next hop active, right? And then I look up. Since I shift, my lookup will be lookup as router 5. Anthony, I'm sorry, we have an issue on the... Okay, well, Anthony is looking for that, and I'm going to telling. So basically, the node coming, and once I know that's sending to me, I'm going to shift on the left side for 16 bits, and then my next hop showing up. And then I do the lookup, right? My forwarding table will be telling me the router 5 is going out into which interface, right? So once the router 5, I do the lookup, it's going out, for example, interface 2, and then it's ready for me to forward the traffic going out of that outgoing interface 2, right? And then that will be finished the forwarding. Is that make sense, right? So MPRS is easy to incoming label, outgoing label, right? Swap, swap, swap. And then why we need a label forwarding is because high efficient. Always 20 bits for the label, MPRS infrastructure, right? You always checking the incoming label, outgoing label, try to find outgoing interface to go away. Now you can see the SRv6 doing the same thing, right? Shift 16 bits, get the next hop, look up which outgoing interface, do the forwarding. That's all. So very simple, very efficient. That's make the SRv6 exactly similar as what we has been introduced for the traditional MPRS. So that's how we finish for the forwarding. Okay. Now we finish the definition SRv6, efficiency for macro seeds, how we flood it, how we do the forwarding, how we do the lookup, right? And now we're going to looking into, kind of the service we can provide. So before that, I wanted to pause for a moment. Is there any question? Okay, go ahead. Okay. That's a very good question. So basically, as you see, when you get the hardware to do the forwarding, it will be introduced some of the latency. I have to go very straight. I don't want to say there's no latency, right? Forwarding you do need, but it's very fast. Put it in this way. You have all the control plane IGP. You converged, right? And then you have the we call the platform independent forwarding information. And this still carry in the RP RSP, right? It's still CPU based. But once you get this forwarding table, you're going to program onto the line card. The line card not using CPU anymore. The line card using NPU. They call the network process unit. The reason is on the NPU, they always just looking for the binary. The binary will be includes for the header, includes the outgoing interface. This is just like a hardware operation, very fast. If you're looking for that NPU level latency, it's microseconds, like 10 microseconds. So there still have delay to answer your question, but really, really fast. Okay. So once we define all the forwarding, let's look into, how the VPN to be supported by the SRv6. So the VPN, basically, we can say we define SRv6 as the transport. Now we're going to kind of to see how the BGP will be, generate or label, and that label will be, carried over by the SRv6 core, so that I can implement a VPN service. It's like whatever we has been done, right, with the MPLS core. MPLS core, if you have the BGP, you can always locate the BGP next hop, and that next hop, the egress PE, can allocate the VPN label for the VPN service, right? And the similar thing is now the egress PE, they're going to have the BGP to allocate for that, microsegments using for the VPN service, so that I can still run the BGP, but the whole forwarding is actually basing on the SRv6 or SRv6 macro seats. Okay. So this is the fundamental high level to introducing for the VPN service, but I will be giving you exactly the service how that running through. Okay, just wait a little bit, let that getting stable. So I think that's probably a little bit electricity inference. Okay, I wanted to get into this topology, so then we can easily to understand what I'm going to introducing for the forwarding environments. Okay, perfect. Now is there. Okay, so this is the topology, right? As we see here, router 12 is the source node. Router 56 is my egress PE, right? And I'm running the VPN between the router 12 and the router 56. And on each side, I have the customer equipment, like a CE device, right? So basically, my VPN or my worth defined between my egress P56 to the CE92, and similarly on the source node, and the CE91 to be pairing with the router 12. And if I have an IPv6 prefix, right? For example, this 2001 DB8 : 192 is my Verve IPv6 unicast prefix. And I'm going to telling on the source on the source node, and I have an IPv6 unicast going to let them to understand is from the CE92, so that the CE91 they can reach into these IPv6 unicasts, but cross the core SRv6. So that's what I'm going to do, right? And I have locator, I have SRv6, and I have BGP running between the router 12, router 56, right? And then I know my BGP next hop going to be pointing to the egress SRv6 node. So I want a BGP to run with SRv6 so that I can do the forwarding will be encapsulate SRv6 into the forwarding lookup. You know, in the bottom, you see the bottom, the light yellow color is actually the IPv6 unicast. This IPv6 unicast is between the P and the CE, right? And the upper one, light blue, is the SRv6 forwarding. So router 56, I defined SRv6 locator. I flooded through the IGP inside the core. It could be ISIS, could be OSPF, so that, you know, the ingress PE, router 12, knowing, you know, to carry over that VPN v6 for that IPv6 unicast, I'm going to encapsulate SRv6 for the router 56, right? So that's how that looks like. The source node is router 12. The destination node is exactly the SRv6 usage of the router 56, right? Makes sense, right? This is looks similar as the MPLS, right? Pretty much same. So SRv6 is not that difficult. It's not that difficult. It's running exactly the same concept. The only different part is the source routing in the core for SRv6. And you probably can see the router 12 enable SRv6. Router 56 is enable SRv6, right? What if in the core, one of the node, I didn't draw a node. Let's say I'm insert a node right now. Just, you know, in the IPv6 fabric, I only understand IPv6, doesn't understand SRv6. Do you think the forwarding will be broken? No. That IPv6 forwarding lookup, as far as the node can do IPv6 forwarding, they can do the SRv6 forwarding. Why? It's because in the core, I don't care. I don't care the SRv6 microsegments, all those defined, right? I only care the IPv6 lookup. So in the core, not have to see that node to support SRv6. That's the beauty. A lot older node, they only understand IPv6 forwarding. You only need to enable SRv6 on the edge, So the core can be only understanding the IPv6. So that's the beauty for this technology. Okay, so you're probably to say, you know, show me something, how you define it, how you want it to carry over, right? So I give a little bit of complicated case, right? But I want you to only focus on the nothing else is the else. So the top two I define by latency, by affinity, it will be using for FlexAlgo. I'm giving this example. You can look into that's the position we introducing for the different domain, right? But let's focus on whatever the else I'm going to allocate a label for the color for the BGP extension community for color 1000, right? So if you don't understand the BGP extension, that's actually, it's there for a long time. It's just like SRv6, they try to pick up to define a domain. It's the same as the BGP community as the traditional BGP, right? What we have been to say is attach a value on our BGP prefix. And that prefix extension, we just leveraged to define as the different domain, right? So then I can use the different color so that later on, my color going to be drive the SRv6 goes to the different FlexAgo domain to do this forwarding. But for now moment, let's just using a traditional BGP prefix and let's use that color 1000. And once you have these BGP routes, right, you put it into the BGP, you say you have the out policy with that, and you attach every single VPN prefix with a color, with that unique value, right? And in the BGP, you're telling them to do the encapsulation or to do the SRv6 encapsulation on the main locator. The main locator is shortest path, IGP shortest path based. That's all, right? Once you're having these, you can say, okay, I'm going to flood it. I have main domain, I have latency domain, and I have affinity domain. So latency and affinity will be introduced by the FlexAgo later on. Let's follow on the main. This main is just like a traditional short IGP path. Okay, so now it pretty much like this. I having a source ingress PE router 12, and I have for outgoing egress PE R56. And as far as I have all those SRv6, microsys has been defined, right? I'm going to flood it. And they know the BGP next hop lookup. Once they have it, they're going to do the encapsulation. How they do the encapsulation? RFC 8996. So that's 86, that's defined in there, right? And you see here on the left side, they have the encapsulation and they have the encapsulation red. What's that red? It's not red, it's reduce. I hopefully they say compress, right? And RED sometimes is make a little bit confused, but I mean, it's reduce, it's compress, similar. So this will be telling you my BGP will be follow this RFC 8986 and do the encapsulation, and I'm going to leverage on the SRv6. And this is exactly what I have defined, what I populate, and what I encapsulate, right? So with that, if I'm checking on our BGP, VPN v6 worth, like for example, worth 1, and I'm going to give this 192. This is the IPv6 unicast. It's coming from CE89, try to populate to the CE81, right? 92 to the 91, right? And they will be telling in the control plane to say they're going to be using the BGP next hop for the router 56, right? Simple. That's purely as the BGP VPN v6. But SRv6 will be telling you which encapsulation they're going to do. Look for those like a purple color, and that's the router 56. And this address is a macro segment address, right? So that's how the BGP encapsulate, because you telling them you want a BGP enable SRv6 locator main, and this exactly follow your instruction to do the encapsulation for the VPN v6 service. Okay, so now the packet will be from source node all the way forward to the egress node, right? And the egress node will be doing the decapsulation. And the decapsulation will be follow exactly the similar, for that RFC. And once you get to this decapsulation, look on this thing. Pay attention to this green color. This green color is exactly the egress PE allocated for the BGP, right? Coming back, coming back, you see here, this is the macro segments for SRv6. The last digit is E006, right? And going all the way to this destination. And this is SRv6 with that function for BGP, right? Because that's the egress P flooded this BGP function all the way to the ingress. And ingress, according to these, to do the encapsulation, once packet sending to the egress PE, they do the decapsulation, right? They know that function is allocated for the BGP VPN v6 for the WRF1 so that they finish the encapsulation and decapsulation, right? That's finished the whole VPN service, right? Okay, hopefully this is go straightforward. That's nothing fancy. It's follow your knowledge, follow your logical thinking, and this is exactly the same thing, but I mean, it's just leverage on the different technology, okay? And I'm finished. This is kind of the service. Now I'm going to look into a couple quite important, in the SRv6, right? Every single protocol, they have to resolve three things, right? Traffic engineering, protection, right? Carry on the service, right? We just finished to say how we carry on the service, but we have to tell. And the SRv6 can do the protection as well. And the protection is goes through, we call the TI-LFA, which is topology independent, loop-free alternative protection path. How this looks like ISIs support LFA like for probably a decades already, right? And the TI-LFA was different. It support all the different topology, and also is the we call the post convergence. What is means post convergence? You see, if you know the traditional MPLS, if you do the fast reroute, right? Once you trigger the protection, they go into the alternative path, but that's not post converged, right? The reason is once the IGP converged, they do the re-optimization. Remember? Re-optimization. Why we need a re-optimization? Because according to the broken topology, right, the backup path not the best, traffic going. They have to re-optimize according to a new converged network, right? But TI-LFA, one of the big advantage, they can do post-convergence. Once they program in the network, the failure happens, you don't need to re-optimize anymore. So that's the beauty for the TI-LFA. And how that works, right? We have this point of local repair, similar, like a fast reroute, local point of local repair, right? The local repair will be trying to calculate the backup path. But in order to do this backup path calculation, right, you see here, right, this is whatever has been defined in the IGP. Very simple. You do per prefix fast reroute for TI-LFA. That's all. That's all you enabled. Everything you offload to the IGP. IGP have an algorithm. They do this post-convergence calculation. And once that calculation is done, this is the example showing here. If you have 1, 2, 3 going to the destination 36, right? And look for these. If you are having a link between 1 and 3 going to be broken, right? You know the path going to 7, going to 5, and going to 3, right? Then what is the post-convergence? Or, the thing is, I'm always just trying to looking which the encapsulation node or protection node I wanted to calculate, I always put in router node 5. Why? Anyone know why I have to program repair node 5, not 7? Because on the 7 is equal path to the node 3, right? Equal path to node 3, right? That means if my IGP converge is not fast enough, the router 7 can send traffic back to this. That's the macro loop, right? You don't want to lose the traffic. That's why you want always the post-converge. The IGP algorithm, they will be always put in the protection node 5, right? Into the protection path, right? Once you program the node 5, it never roll back. There's no macro loop anymore. Because onto the node router 5, they always forward to the router 3 and will be heading to the destination. That's the TI-LFA, right? I know there are a lot, details, but, you can always pick up later on. The most important thing is just the post-convergence and why we put router 5 as the protection nodes. And here is telling you, if you show routes for that destination on the router 36, the green color is the protected link. If this protected link goes down, you have to go to the backup path. And that backup path has been calculated by the TI-LFA, right? And as you see, this TI-LFA protected node is node 5 macro seeds. And that's how these things will be ensured post-convergence. Okay, so there are a few more, different ways to checking either from IGP ISIs, right, or the SAF table. SAF table is the forwarding table. It's exactly has been programmed into the line card NPU, right? So as you see here, my protect path in the green color and my backup path, it always pointing to the protection node 5, other than router 7. The router 7, I always telling my egress interface heading to router 7. But goes to the router 7, they will be looking up the protection node 5. And until reaching to the node 5, then the protection always is the post-converged. Okay, so that's the protection, right? I know this is a little bit of detail, and hopefully this is giving you, most the key message, the key important thing. And then next thing we're going to talking about traffic steering. Traffic steering is also called the traffic engineering. Okay, so in the network, you can define the policy, travel the different paths, right? In the traditional MPLS, there is a terminology called the PBTS. Anyone know? Policy-based tunnel selection. How you do that? You use, the COS, right? 1, 2, 3, 7, so that you can check up for the IP header as far as you matching, and you're going carry by that tunnel associate, right? So that's the PBTS in traditional MPLS. SRv6 can do the same thing. What are we going to introducing here is we have upper pass, short IGP, bottom pass, low latency. And what you can do here is basically you want to label the packets on the incoming side, on the ingress side to marking. Because in the SR policy, we only recognize the forwarding class. So on the incoming ingress side, we can marking the forwarding class. And I can, according to the IP header DSCP bits, right? Or access list. And I can, based on that, to marking my traffic. For example, If I'm marking my traffic forwarding class 1, just giving example, they will be follow the shortest IGP. And if I'm marking my forwarding class 2, I'm going to use the bottom pass low latency, right? So here is the, the policy map. On the right side is the class map. The class map try to match the DSCP and just make a marking. The marking is actually in the policy to say, according to this class map, I'm going to marking for those packets, either for forwarding class 1 or forwarding class 2, right? With that, and I define my SRv6 policy, and I can telling them for a certain traffic, let them to follow with the forwarding class 1 or forwarding class 2. But what is auto route? Is that sounds familiar? The MPLS traffic engineering, they are using auto route announce, right? Why they need auto route announce is because they need to telling the IGP to select which tunnel to forwarding traffic, right? And they are using the same terminology because now SRv6 is IGP. But in order for people to carry on the traditional thinking, they always using auto route and with the forwarding class. So that with that forwarding class, as you see, and checking for that policy, they will be always pick up, according to the marking to forward traffic to the different, paths, right? So we talking about these like, traffic steering, right? So we can do the protection, we can do the traffic steering, right? And that's exactly implement what we has been, using on the traditional MPLS world as well. Okay, last thing, but not the least thing, FlexAlgo. I'm going to introduce these because that's new. Traditional MPLS, no such thing. We do support affinity, but we don't define as a sub-topology in this way, right? Affinity, we always have include, exclude, right? So then you can have the bigger topology, but you rely on the affinity to include a path or exclude a path, right? It's the same MPLS TE database. It's the same MPLS TE database, but you use include, exclude to do that, affinity. But here, the FlexAlgo is the different. It's a new terminology. Let me just get into that very straight, right? So this is your topology on the upper right corner, right? You have upper data path, green color, and you have bottom data path in red color, right? Let's assuming the upper one, either the shortest path, or you can define affinity for color green, right? And the bottom one is the low latency, right? And you have the two way to implement. You can use traditional MPLS way, always trying to use affinity to do the include, exclude. But that's not efficient. Why? Because the calculation have to calculate the whole topology for all the nodes to calculate a path, right? But what if you define a subdomain? For example, you have subdomain with the upper green nodes and a subdomain for the bottom red domain. And when you do this calculation, the path calculation only consider those nodes as the subdomain. So you will have more efficient path calculation. So that's how the FlexAlgo get into this picture. And the configuration is pretty simple. That means you define this, locator, and the locator will be assigned a different prefix for the different subdomain, right? And once you have this subdomain defined, and you flood it into the IGP. But The important part, what I try to see here is probably we can see, sorry. Yeah, this one. This is a very important information. All the nodes you have to define which flex algo you're going to participate. For router 12, it have two default flex algo, 0 and 1. Every node is already included in the default flex algo. And on the edge, if you wanted to have the selection go the different paths, you have to let the router 12 to be participated for both algorithm, like 128 or 129. One is the short IGP path. The other one is the latency. But for router 1 on the top, they only need to participate for that green domain. I believe that's 128, right? And for the bottom node, that's the node 3. I'm sorry, node 2. They only participate for the FlexArgo 129, right? This will be helping them to create a subdomain. That's why we have a subdomain topology, right? Because on these FlexArgo, they only include a sub-topology nodes. And when you do the path calculation, it will be much more efficient. Okay, so we introducing for this IGP configuration already, right? This is similar as what we introducing for the domain, for the main domain as well, but it just introducing additional prefix for the same node for the different purpose because we wanted to flooding for those subdomain information. Once we have that, right? And if you have to checking for the FlexArgo, now you can see, right? If I'm checking for the IGP ISIS for the topology FlexArgo 129, and you can see the nodes showing here is a subset of the nodes. It's not every nodes, right? It's the subset nodes. And you can see to reaching the FlexArgo 129, they're going to reach out. The interface is the Gigi 0002, right? From the router 12 on the source node. And if you're checking the FlexArgo 128, is actually coming out of the interface is Gigi 0001, right? So this giving you for the different FlexArgo, they will be using the different data paths for the forwarding, right? And later on, if you checking these, according to the different prefix, which has been advertised by the different FlexArgo, you can see for 128, for that SRv6 prefix, they going to follow exactly the data path going out from the Gigi 0001, right? And if you're looking for another FlexArgo domain, they will be going to the different outgoing interface, which is the Gigi 002. So as you see, on the router 12, we have two forwarding plane. The top one is short IGP. The bottom one is the low latency. And these, if you, according to the FlexArgo, that's exactly, the different data paths will be showing to you. If you're looking for the FlexArgo 129 for low latency, and that's exactly they will be telling you the outgoing interface going to the bottom data path. And previously, for the the short IGP, they will be pointing you to the upper data path. So that's how the FlexArgo, it's the similar way to define the locator, but it will be like the nodes to decide which algorithm they're going to be participate, right? That's how the IGP config to say, I'm going to participate in the FlexArgo 128, and that's the green nodes, right? And I'm going to generate another routing domain is for the red nodes, and that's the IGP defined and flooded, and that's how the forwarding lookup will be showing up in the SAP forwarding. So I know that's rough. That's pretty much what has been done for today. And, I'm going to be ready for some question, right? And if you have question for now, you can ask me now, or I'm going to be stay here until the timing for this room. And if you wanted to have some private discussion, it's perfect okay as well. Okay, thank you. Thank you, everyone. Or you can come up to here if you want to have some private discussion. Yeah. I am not very good for the other one. But, they are so what is the position of the strength related and they are not